very excited to be here in the land of Celine Dion, where finally this title can reach its intended audience. So today I'll be talking about dwarf galaxies, near, far, and wherever you are. So across a range of distances and resolutions. Before I get into it, I just want to take a quick moment to acknowledge that there are a lot of communities who have helped make this work possible. So throughout this talk, I'll be talking about my scientific collaborators, as we all should. Scientific credit is important. But there are also other communities who help maintain me and maintain my work. So this includes the fact that I live and work on land that is traditionally the unceded homelands of the Pocumtuck Nation. I think this is particularly noteworthy because I work at Amherst College, and Lord Jeffrey Amherst was a known genocidal person. And then it's also important to note that we are here on the traditional lands of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. So throughout this talk, I'll also be discussing astronomical data that were taken with the Keck telescopes in Hawaii. And so in many ways, my science itself is also only possible because Mauna Kea was dispossessed from Kanaka Maoli, or Native Hawaiians. And then finally, there's a lot of other folks. So folks like Andrew here, who helped organize this whole thing, staff, maintenance workers, cafeteria workers, janitorial staff, all of whom help maintain me and maintain my work. And so a lot of these folks don't, I think, get the credit that they deserve. And so I'd like to shout them out now before we get started talking about science. Oh, thanks. So thank you for taking the time to acknowledge all of these folks with me. Okay, so the main takeaway of this whole talk, dwarf galaxies are useful. If this is the only thing you get out of this talk, great. We're done, you can leave, you can go get the cookies ahead of time. If you want to stay and keep listening to me talk about dwarf galaxies, I should say when I mean dwarf galaxies, I mean things that have stellar masses of around 10 to the 9 to a billion solar masses or so. So we're talking LMC mass or smaller. And they're useful for a couple of reasons. So first, they're logistically useful in the sense that there's just a lot of them. For every Milky Way mass galaxy, there are tens, hundreds, depending on how you count them, possibly thousands of these small dwarf galaxies. And they're super diverse. You can tell just by looking at them. Oh, it's a little hard to see the pictures, but here's a collage of random dwarf galaxies in the nearby universe. And you can tell visually already they look quite different. So some of them, for example, have a lot of gas. They have almost spiral-like structure. Some of them just kind of look like oversized globular clusters. So even visually, they're different. But then if you look at their physical properties, they also span a huge range of star formation histories, metallicities, masses, and that makes them really useful as laboratories, right? Because you can pick a single variable to change and then hold everything else constant. So they're nice, nice laboratories for hypothesis testing. On top of that, they're relatively simple in some ways compared to their more massive counterparts. So if you look at a galaxy like our Milky Way, for example, our Milky Way has a lot of moving parts. As many folks here know, it has a thick and thin disk, it has a bulge, it has this outer stellar halo, it has lots of streams, which are not even shown in this artist's rendition. And all of those different components have their own accretion history, their own star formation history, et cetera. And so disentangling the evolution of all of those components is really difficult. But with dwarf galaxies, to some extent, they can be treated as like single zone blobs. And so then that makes them, in some ways, a little easier to physically interpret than more massive Milky Way-like systems. So logistically, dwarf galaxies are useful. But then from an astrophysical standpoint, they're also interesting and useful. So for starters, in our current picture of hierarchical structure formation in the universe, we're fairly certain that dwarf galaxies were among the first galaxies in the universe to form. And then they merge together and form slightly more massive systems, which then collapse into more massive systems, et cetera, until you get something like the Milky Way. And we know today we see signs of the Milky Way actively accreting dwarf galaxies and continuing to build up mass over time. So if we want to understand how galaxies like our Milky Way came to be, we have to understand dwarf galaxies, their formation and their evolution. And then if we zoom in even further and look at really what makes up a dwarf galaxy, or really any galaxy, dwarf galaxies are made up of stars. They're made up of other stuff like gas/dust, the ISM in general. And then there's also a lot of dark matter. And so dwarf galaxies, are constantly, the baryonic matter in a dwarf galaxy is constantly cycling between these two phases. The gas turns into stars. The stars live, produce heavy elements, and then die and release those heavy elements along with a lot of energy and momentum back into the gas of the galaxy. So there's constant sort of baryonic cycle within a galaxy. And they're not closed systems either. So there's also gas inflows and outflows as dwarf galaxies interact with their environments, with their neighbors. And all of these different processes can help tell us something astrophysically. So for example, we know that dwarf galaxies have really high mass to light ratios compared to more massive systems, which could make them useful as potential probes of lambda CDM. So we can actually use them as sites to do direct detection of dark matter as potential targets. The numbers, like the general population characteristics of dwarf galaxies can help constrain cosmology. So lambda CDM, for example, makes specific predictions about the numbers of dwarf galaxies, their density profiles, their masses. And so we can use them to actually test lambda CDM. And then dwarf galaxies, many of them are thought to be fossils of reionization in the early universe. And so dwarf galaxies in many ways are local analogs of high redshift systems. And so we can use them to tell us something about what conditions were like, to some extent, what conditions were like in the early universe. And if you're interested in high energy stuff, I didn't even put this on there, but dwarf galaxies are thought to be hosts of several particular types of high energy events, like short gamma ray bursts, potentially gravitational wave events, maybe. And so there's a lot of interesting reasons to care about dwarf galaxies. And that's even before you get to the galaxy part of it. The fact that galaxy evolution theories are often tuned to match galaxies like our Milky Way. We don't have a good handle of what happens in low mass systems. So dwarf galaxies provide a really important test of a lot of our basic theories of galaxy formation and evolution. So dwarf galaxies are great. They're super useful. They're super interesting. Hopefully, no matter what area of astronomy or physics you're interested in, there's something that we can learn from dwarf galaxies. But there's one potential downside here, which is that dwarf galaxies, for all that I've said that they're relatively simple, they're also relatively susceptible to peer pressure. They're strongly influenced by their environments. And that's a problem because dwarf galaxies are also small and faint, which means that for the longest time, and up until quite recently, we've basically only been able to observe dwarf galaxies right next to us. So the most well-studied group of dwarf galaxies are the dwarf galaxies in our very own neighborhood, in our local group. This is both a small sample size, so not great, maybe only 100 dwarf galaxies or so. And it's also a potentially unique environment, right? If we zoom out of our own local group, this is a nice artist rendition of the larger local volume, we see that our local group is sort of the suburbs. This is like the Scarborough, I guess, of the local volume, right? It's not downtown Toronto. It's not way out in the Alberta. I don't know. And so it's only one particular kind of environment. We cannot go to Scarborough, pick a random suburb of like 100 people and suggest that these 100 people are representative of all of Canada. And in fact, recent work has shown that it's very unlikely, looking at galaxies that are like the Milky Way, it seems pretty clear that our Milky Way is not even representative of other Milky Way-like galaxies. There's a huge, diverse range of different types of Milky Way-like galaxies. The good news is that we're getting better. We have more instruments, we have more surveys. I'm going to mention some that I think some folks here work on. So for example, LSST and at Rubin is going to be a photometric survey that is really reaching unprecedented depth. So here's a really nice graphic. If you can't see the axis labels from the back, this is stellar mass and this is surface brightness. So from SESS, which has been for a very long time our flagship galaxy survey, we are now beginning to push orders of magnitude fainter galaxies. We'll start getting dwarf galaxies all the way out to redshifts of, here it's 0.25, which I recognize for some of the high redshift people here is a very small number. But for those of us who have been limited by megaparsecs for far too long, this is actually a really big number. So we're getting all of these incredible photometric surveys. We're getting all of these large-scale spectroscopic surveys, which all have acronym names like DESI, MOONS, PFS, which are getting, another, tens of thousands of spectra of dwarf galaxies across a huge range of environments. And then on top of that, we have all of these, what I like to call bespoke surveys. So sort of smaller surveys that are focused on dwarf galaxies in particular environments. So for example, the Fornax Deep Survey is focusing on dwarf galaxies in clusters. Saga and ELVES are both dwarf galaxy surveys focusing on satellite galaxies of Milky Way-like systems. All these smaller bespoke surveys, between all of these, we'll get a really nice complementary view of dwarf galaxies across a huge range of environments, which is incredible. And then on top of that, we have the big guns. We have Gaia, which is starting to observe the nearby universe, including our next door neighbor dwarf galaxies, in more detail than ever before. So individual stars. And then we have JWST, of course, which is starting to look deeper than ever before, trying to find dwarf galaxies in the very early universe for the first time. So it's a good time to be a dwarf galaxy astronomer. Potentially one downside is that we have not yet figured out how to solve one of the fundamental problems plaguing galaxy observations, which is that nearby galaxies and distant galaxies fundamentally look very different. So visually, can anyone tell me why they're different?
Resolution.
Resolution, yeah, okay. So in nearby systems, we can actually resolve individual stars. In high redshift things, they mostly just look like blobs of light. And this is a fundamental limitation. There's sort of no getting around this. Our ability to resolve individual stars is very, very limited. Again, basically just the local group and maybe slightly outside of it. For integrated everything else, for all of these massive surveys I've talked about, the vast majority of them are looking at integrated light from galaxies. So we have a trade-off, right? We get increasing sample size the further away we look, right? We can look at redshift evolution, et cetera, but we lose spatial resolution. And so what a lot of my work is about is trying to bridge this gap with integral field spectroscopy, IFU spectroscopy. The idea is that this is a nice middle ground between resolved systems and these distant integrated light systems because it's kind of crappier than both simultaneously. So on the one hand, we can use IFU spectroscopy. So for the folks who are not familiar, really quickly, IFU spectroscopy is like taking an image, except at every single pixel, you get a full spectrum. So you get both spectral and spatial coverage and limited spectral and spatial resolution. And that can be good because it can actually help us test the effect of looking at resolved systems versus unresolved systems. We can essentially blur a galaxy that looks like this and see if we get the same thing out from IFU spectroscopy. And this has been done a couple times. So not often, and we'll get into the reasons why in a little bit, but a few studies have started looking at trying to measure the same properties for dwarf galaxies from both resolved stars, so doing things like color magnitude diagram fitting, et cetera, and then from fitting models essentially to integrated light measurements from IFU data. And this is really hard to do. Again, we'll get into why in a little bit, but essentially it's only been done for very small handfuls of galaxies, typically individual galaxies, like one galaxy at a time. And only for certain properties that people are particularly interested in, like metallicity or age or star formation histories. But we can maybe do better. We can start looking at things like masses, dynamical measurements like kinematics. So there's a lot of room for more work just in this particular space. On the other hand, we can also use IFU spectroscopy to compare against really distant high redshift galaxies, so to bridge the gap on the other side. And in particular, what I worry about a lot are aperture effects. So this is a big problem when it comes to spectroscopic surveys, including SDSS, including DESI, and a lot of these big fiber-fed spectrographs. Because dwarf galaxies are so close by that if you put a fiber or a slit on it, you actually end up missing a lot of the light from the galaxy. And so you get these aperture effects, which have been studied fairly well because as soon as SDSS came online, people realized this was going to be a problem. But this has mostly been focused on massive galaxies. And so there are actually not that many studies looking at aperture effects in dwarf galaxies. So I think this is the main takeaway, really, which is that if we want to make the most out of all of these upcoming galaxy surveys, this huge, unprecedented wealth of low mass galaxy data that we're about to get, we need to build and test this resolution ladder. We need to understand the systematic effects that plague us going from resolved data to unresolved data. And we have to test every single rung on this, what I so-called resolution ladder, which I've shamelessly stolen from the distance ladder people. So I just want to pause here. Oh, sorry. Sneak preview. I just want to pause here and check, are there any questions before I move on to the next part of this talk? I've explained everything perfectly. You all agree that dwarf galaxies are incredible? Great. So now you get to decide what I talk about. I couldn't decide, and so you get to pick for me. We're going to do a show of hands. I can either talk about sort of building this resolution ladder with this survey called the DIVE survey, which is an IFU survey, or we can talk about testing different parts of this resolution ladder using galaxy simulations. So I'm going to, you can think in your brains for a little bit, make significant eye contact with the person sitting next to you so you can decide what you're going to vote on. All right, let's do a show of hands. Who wants to hear about number 1? And who wants to hear about number 2? Oh my God. Okay, I do think.
Oh, we've got some deciding votes on the chat.
Oh, we got some votes on. Okay, all right. Chat says number 1, Sound is perfect. Oh, incredible. It's all me. Okay, let's do number 1 first, because I do think there were more hands for that, and there will probably be time for the second one also. Okay, so the DIVE survey is one of these bespoke galaxy surveys, and it's really focused on the loneliest galaxies in the universe, which is what I put in all of my grant and telescope proposal titles, because it sounds great. So this resolution ladder really requires us to get a lot of IFU data, which is hard because IFU data, because again, you have multiple spatial pixels and then you also have the spectral direction. You can imagine the observational time requirements are exponentially higher for an IFU survey compared to a photometric or a spectroscopic survey. And so all of these IFU surveys that are targeting dwarf galaxies are targeting sort of small, bespoke samples of dwarf galaxies. So we have some that are focused on the most massive dwarf galaxies. We have some focused on dwarf galaxies in clusters or that are satellites of other galaxies. And then we have my personal favorite, because my name is attached to it, the DIVE survey, which is focused on dwarf galaxies in cosmic voids. And understanding all of these environments is really key, because we know that environments affect dwarf galaxies. And so understanding the effect that that has on the detailed properties of dwarf galaxies is kind of important, and probably will be very useful as we start to try to interpret LSST data or DESI data in the future. Okay, so the DIVE survey is a great acronym, which stands for, just kidding, I'm not talking about it yet. The DIVE survey, the V you might have guessed, stands for voids. Cosmic voids, I think, it's pretty clear why they haven't been historically great places to do extragalactic science, because there's not a lot of stuff there. So dwarf galaxies have on order of magnitude 10% of the density, number density, mass density of the average density of the universe. And there's sort of these big underdense regions that are not totally empty. So even in dark matter only simulations, we can see that there is structure still inside of voids. And there's been a lot of work recently trying to figure out what that structure is statistically and what these voids look like. But if you look inside of those voids, there are also galaxies. And we know this, we've seen them, we can see them with SDSS. For folks who study high redshift galaxies, these might look kind of familiar because they're irregular looking, they're blobby and star forming and blue. And these are all things that we think high redshift galaxies probably look like also, for galaxies in the early universe. And so these dwarf galaxies in cosmic voids are a really nice sample for a lot of reasons. So first of all, we can compare with our own local group. They're a nice sort of control sample because the dwarf galaxies in our local group are constantly being influenced by our Milky Way. The dwarf galaxies in a cosmic void are not, sort of inherently. They're far away from any massive galaxies. And so they're a nice control sample for these environmental effects. We can also use dwarf galaxies in voids to compare with simulations. So as many folks know, simulations are hard, especially given the huge range of spatial scales that we need to simulate. And so galaxy simulations in particular, none of them can resolve individual stars in a galaxy. None of them can. And so it's impossible to simultaneously have extremely high resolution within the galaxy and also the rest of the galaxy environment. So a lot of our highest resolution dwarf galaxy simulations are of isolated dwarf galaxies, because we're just pretending that the rest of the environment doesn't exist. So if you want to do an apples to apples comparison with the simulation, you also need to look observationally at galaxies that don't have things around them, isolated dwarf galaxies. So dwarf galaxies and cosmic voids are a great way to do that. This is just a nice video from the fire simulation, which I picked, but I also think looking at it now, I'm so sorry if you have red-green color blindness. I don't think this is going to look very exciting to you. But these kinds of simulations are another nice comparison sample for void dwarf galaxies. And then finally, as I mentioned, dwarf galaxies are very similar in many ways to galaxies in the early universe. And void dwarf galaxies are particularly similar in the sense that they are small and low mass and they haven't interacted much with other stuff. So in some ways, their evolution has been slowed compared to dwarf galaxies outside of voids. And so that makes them a nice comparison sample with galaxies in the early universe, high redshift JWST-like things. Okay, so now that I've convinced you that dwarf galaxies in voids are a particularly useful sample to study, hopefully, I can now bring up my acronym that I've been very excited about, the Dwarfs in Void Environment Survey, the DIVE survey, which specifically targets void dwarf galaxies. Identifying voids in any kind of survey is difficult, but there are various algorithms to do so based off of galaxy catalogs. So we use this particular void finder algorithm, which geometrically selects voids from SDSS. We pick some of dwarf galaxies inside of those void regions, and then we end up with a final sample, which is very small, but remember this is a pilot sample, and eventually somebody's going to give me more telescope time to expand it, of around 20 void dwarf galaxies, and then 10 galaxies, dwarf galaxies that are not technically in voids, but are pretty isolated. They're not satellite galaxies. And so they're sort of a control field sample to test the effects of large-scale environment versus just local isolation. Okay, so I'm going to talk very briefly about some of the first results from this DIVE survey, and then I'll talk about some stuff that I have been attempting to get to build an army of undergrad students to work on. With limited success so far, but it's going to happen. Yeah, real quickly. Chris, yeah?
Void.
Yes.
Is the mass distribution of galaxies different? So are the dwarf galaxies the largest galaxies you like to define in the void? Or is it a really good question?
It's one that we don't know the answer to yet. So partly because SDSS was mass incomplete. And so to date, SDSS has had the best coverage of a lot of these void regions. So the short answer is probably they're more dwarf dominated, but by how much we don't know. And it's not clear what the total mass function looks like because we're so mass incomplete. Yeah, good question. Any other questions about voids before I keep going? Yeah.
But when we look at extreme and high redshift, because you want to compare the dwarf galaxies in the voids to very redshift, how do you know if the dwarf galaxies at very redshift are the ones that are also in voids, or if they're going to end up being voids?
Yeah, good question. Oh, I also forgot I was supposed to repeat the question. I'm so sorry to the folks on Zoom. The question was, for high redshift dwarf galaxies, how do we know if they're going to end up in voids or not? The answer is probably not. Well, probably not, because the things that are dwarf galaxies at high redshift are likely the progenitors of Milky Way mass galaxies today. So to some extent, there is no real local analog for a high redshift dwarf galaxy because most things will not stay dwarf galaxies. And the things that we're observing now with JWST are the brightest ones. They're the ones that are, because Malmquist bias, selection bias, we are effectively selecting the things that are most actively star forming, and as a result are most likely to build up mass. Yeah, that was a good question. Also, we don't understand anything about the high redshift universe. So we don't know the IMF, the initial mass function at those high redshifts. Dust is probably totally different. We don't know what dust looks like at all. The effect of low metallicity, all of those things actually make it really difficult to do any sort of real direct comparison. So that's a good point. When I say we can compare these things to high redshift things, I mostly mean their merger histories are probably relatively similar at this point. But almost everything else is probably still pretty different. Yeah.
So when we say high redshift up to what? Are we talking about?
That's a good question.
Can you repeat it?
Yes, when we say high redshift, what do we mean by high redshift? As you've seen earlier, to me, high redshift is anything above redshift 0.1. But in reality, I mean, JWST is starting to find dwarf galaxies out to redshifts 1 to 3-ish. The stuff at very high redshifts, so the redshift 9 stuff, those are almost certainly anomalous and not representative of actual dwarf galaxies at those high redshifts. Yeah. Good questions. Cool. All right, so I'm going to start talking about some of these very first results from DIVE. So one of the first things we wanted to study was stellar kinematics. Because again, as I've said, most of our understanding of dwarf galaxies is really based on the local group, because these are the only things that are close enough that we can actually see how the stars in these galaxies are moving. And so based off what we know about our local group, we've seen that there's a bimodal population, dwarf spheroidals and dwarf irregulars. Dwarf spheroidal galaxies in the local group are gas poor. They are spheroidal, hence the name. They're not actively star forming, whereas dwarf irregular galaxies are not spheroidal and are irregular looking. They have a lot of gas, they're actively star forming. And so any theory of dwarf galaxy evolution and formation needs to be able to explain the difference between these two populations. The good news is that this is actually really easy. It's just the distance from the Milky Way. So dwarf spheroidal galaxies are essentially inside of the virial radius of the Milky Way and have been impacted tidally. And so they've been tidally stripped of their gas, and that's why they're not forming stars anymore. That's why they look like like overblown globular clusters. Dwarf regular galaxies are far enough away from the Milky Way that they've been able to retain their gas and continue actively forming stars. Easy peasy, problem solved. The only downside is that, so that explains the gas in these galaxies. The stellar kinematics of these galaxies is not actually super clear. And so one potential explanation to explain, why these two populations are different as stellar systems is this theory called tidal stirring. So it's this idea that in sort of classical galaxy formation models from like I'm going to say a decade and it's going to be wrong, the 90s, 80s. At some point, people thought, okay, galaxies form as these relatively thin rotation-supported disks, and then they puff up over time. We know now this is almost certainly not true, but this led to this hypothesis called tidal stirring, in which a dwarf regular galaxy is a rotation-supported thing. So the rotational velocity, the ordered rotation, is greater than the random motions, which are characterized by the velocity dispersion. And the idea is that as a dwarf regular galaxy has tidal encounters with the host galaxy, a more massive host, it puffs up into this dispersion-supported system, where now the velocity dispersion is higher than the rotational velocity. So people decided to check this fairly recently. Ideally, if this hypothesis was true, we should see something like this. The ratio of the rotation velocity to the velocity dispersion should go up the further away you get from a massive galaxy. So within the virial radius, you expect relatively low V over sigma values. And as you move away, as your galaxies become more rotationally supported, you get more disky-like things. Yeah. So people decided to check this for the first time in 2017 and found that actually, regardless of how far away you get from the Milky Way, almost all of the dwarf galaxies have relatively low V over sigma. They're all kind of puffy looking. None of them are really disks. And so they saw this both in the local group. They showed this in simulations, mostly with the FIRE collaboration, but other simulations have since shown this. And so this begs the question, is it just because of our Milky Way? Again, is our Milky Way special or is something else going on? Can you extend this x-axis even further and eventually get a dwarf galaxy that looks like a disk if you just move far enough away from other massive galaxies? So void dwarfs helpfully extend this x-axis out to like megaparsecs, because that's the size of a typical void. So that's exactly what DIVE is good for, because we have both this combined spatial and spectral resolution. We can make these beautiful maps of the stellar kinematics of these systems by fitting stellar population models to the observed spectra. We can then get the line of sight velocity distribution across the galaxy. So you can see this is the line of sight velocity. This particular galaxy is redshifted, moving away from us at the top, blue shifted, moving towards us at the bottom. So it's a nice rotating disk thing. And you can also measure the velocity dispersion across the entire galaxy. So if we put all of this together and just remake that same plot from before, except now all the purple points are these void dwarf galaxies. This is now on a log scale, so we're moving like really far out from massive galaxies. We see that these things are also pretty puffy. None of them have particularly high V over sigma values. So for comparison, the Milky Way has a V over sigma of like at least 4, depending who you ask, anywhere between 4 and 20. But it's way up here off of this plot. And all of these dwarf galaxies are much puffier, much more dispersion supported. Chris?
Can you discern any upward trend from 10.3 to 10.4, or is that just my imagine?
Yeah, that's a good question. I think the sample size is not good enough to tell. And we also it's hard to measure rotational velocities past a certain point. So because of our spectral resolution. And so our velocity dispersion measurements become uncertain once you get to the really low values down here. That's a good question. So it's possible there's an upward trend. This is what I keep writing in my telescope proposals. And eventually we'll get more data and we'll find out. And then I think there's a slightly more convincing trend though. If you change the x-axis, instead of distance from a massive host galaxy, if you change it to the mass of the stellar mass of the galaxy itself, you start to see, this is, I think, a slightly more convincing trend. We did some statistical tests. This is actually, I realize by eye, chi by eye is maybe not the best, but statistically, this is also a stronger correlation. So this suggests that there's some mass dependence. You cannot get a stellar disk below a certain mass. There's still some work to be done, in part because, as I said, the Milky Way is 10 to the 11 in stellar mass, and it's way up here off this plot. So connecting these galaxies to the Milky Way is still an open question. But it's one that I think we're better equipped to answer now if we use IFU surveys like these in the future. All right, so there's a lot of other things. Let me stop there really quickly. Are there any more questions about the kinematics stuff? Yeah.
In the voids, are those all isolated from other dwarf galaxies too, or are they like binary dwarfs?
Yes, what a good question. The answer is we don't know. Because we used SDSS to select these dwarf galaxies, down to the SDSS mass limit, which is like 10 to the 7 in solar mass, we are pretty sure that these things are isolated. But below that, it's entirely possible that these could be like the LMC or the SMC and have their own like little hordes of satellites attached, which could be affecting their evolution too. It's a great question. And it's one that we don't have a good answer for. Even with LSST and DESI, I don't think we'll have the coverage needed to tell for sure. Yeah. But in the meantime, as I continue to hope that's, oh wait, there's a question in the chat. How robust are the kinematics for the 10 to the 4 to 10 to the 6 solar mass objects? Yeah, so these are the 10 to the 4, 10 to the 6 ones. These are all in the local group. So the green and the orange points are local group galaxies. The green ones are ultra faints. And so these are all from resolved stellar measurements. So there is, particularly when you get down to around 10 to the 5 and below, you start to run into uncertainties like binary stars, which are not well understood and can affect the velocity dispersion. Because a lot of the green points in particular are based off of sample sizes of like 20 stars. And so if a couple of those are binary stars, that will actually affect your kinematics tremendously. But the uncertainties are more or less captured below 10 to the 4, I think fairly well in the error bars. Does that answer your question, Jacqueline? I'm going to assume yes. Cool, thanks. Okay. So we've been able to use Dive to is that another, sorry, is there another?
She said thank you.
Okay. So we've been able to use Dive to answer questions about stellar kinematics. But the nice thing about IFU spectroscopy is it's just incredibly rich. There are all these things that we can do with spectra. So we can do things like not just look at stellar kinematics, but gas kinematics. So in IFU surveys of more massive galaxies, people have shown that there are some galaxies where the gas and the stars are just not moving together at all. So for example, here, this is gas velocity in this column, stellar velocity in this column. In these galaxies, for example, the gas might be moving perpendicular to the stars, or even counter-rotating. And the vast majority of explanations involve galaxy interactions of some kind, so galaxy mergers. Void galaxies are probably less influenced by galaxy mergers and other interactions. So we actually have begun, I'm working with a PhD student who's actually started to find some of these misalignments, even in void galaxies. And so there needs to be a different explanation for these misalignments that we are not sure of yet. Some dynamicists should come talk to me about it. We can do sort of more out there things. We can look for black holes. This has become extremely popular lately, trying to use IFU data to look for intermediate mass black holes and AGN in dwarf galaxies. So some number of multi-wavelength surveys, radio surveys, X-ray surveys have identified what seem to be this population of wandering black holes. So black holes, compact sources that are producing X-ray or radio emission that cannot be explained by star formation, that are outside of the center of a dwarf galaxy. So these wandering black holes, if they really are black holes, we could do some kind of like BPT-like diagram looking at emission line diagnostics to try to figure out if the gas near this black hole has been ionized by black hole accretion or by something else, like star formation. So one of my recent thesis students, Eliza, who is now going to be a PhD student at UC San Diego, tried to do this. The answer is inconclusive, but might pave the way for future follow-up studies, optical IFU follow-up studies of a lot of these potential like intermediate mass black hole candidates. And then finally, I save this for last because this is kind of always a can of worms. But in theory, you can use emission line diagnostics to measure the gas phase metallicity of dwarf galaxies. And so you can compare the chemical evolution of dwarf galaxies inside voids with the chemical evolution of dwarf galaxies outside cosmic voids. And some people claim there's a difference, and some people claim there's no difference. And all of these surveys involve SDSS-like fiber spectroscopy. So they're all subject to these aperture effects. So IFU data might be one way to hopefully address this question in a slightly less systematically biased way. All right, so to summarize, this dive survey is a really rich IFU data set. It's one of many that people have been trying to develop to essentially build this resolution ladder. We've already shown that you can get really interesting science results just from trying to fit the stellar continuum of these galaxies. And then there are all these other open questions about black holes, about gas and stellar misalignments, about chemical evolution that we can try to answer with such a rich data set. All right, so I'm going to pause here again, ask if there are any questions. Yeah.
Going back one slide. When you say non-void, should the picture in my head be the filament? Or...
Yeah. So these are things that are identified as being in walls or in filaments. Yeah. Any question? Yeah.
Can you say more about how these aperture effects manifest and whether you I mean, I would just if people are worried about an aperture effect in the survey, they would have tested for it by looking at individual objects in more detail with more apertures. Is that...
Yes, that's a good question. So the answer is that, okay, so the question was about aperture effects and how they can manifest. The easiest way is if you have a metallicity gradient of some kind, for example. So if the core of the dwarf galaxy is more metal rich or more metal poor than the outskirts, which it can be for many reasons. So we've observed both positive and inverted metallicity gradients in dwarf galaxies at all redshifts. Some of it might be due to feedback and other baryonic effects. Some of it might be due to galaxy interactions. And that would give you a biased measurement of the metallicity in either direction. The biggest difference between these two surveys and the reason that they find such different results is because they've defined voids very differently. So that's a whole separate can of worms about how to actually pick a galaxy in a void. But the aperture effects themselves, people have studied them to some extent. So for example, if you put a long slit rather than a fiber, you can get a sense of what the radial gradient will be, at least in one direction. And people have done that. So we know that gradients are a thing. We just don't know, like if you only have a fiber and you're only putting it in the center of the galaxy, which is what most galaxy surveys end up doing, you don't know what the effect is. Yeah.
What do you mean by wandering black holes? It's wandering with respect to
so
maybe the stellar distribution, but what about what maybe you know nothing about the dark matter distribution?
Yeah, the question was, what do we mean by wandering black hole? Is it wandering with respect to the stellar distribution, to the dark matter distribution? We don't know the dark matter distribution in most of these galaxies. There have been some follow-up studies with CO for a very small handful of void dwarf galaxies to try to trace the dynamical mass and the dynamical radial profiles of these things. But we don't know. With respect to the stellar distribution, so this dwarf galaxy in particular has a pretty clear central bulge, and this compact radio source is not in anywhere close to the central, the starlight weighted center of this galaxy, which does seem to be a pretty clear morphologically distinct thing. Does that make sense? So when people say wandering, they just mean outside of the central, however many kiloparsecs they've defined.
And it has to be an AGN, but
that's what the current thinking is. So I mean, these have been identified in both radio and X-ray, and their radio and X-ray fluxes are high enough that it's actually really difficult to explain them with star formation. So the leading theory is that they are AGN. There's this whole series of papers where people have tried to use optical emission line diagnostics to find dwarf AGN and mostly failed. And so we're pretty sure that the same techniques that we use to find AGN in high mass systems are not going to work in these low metallicity dwarf galaxies.
Color.
Yes, exactly. This is why we think we didn't find anything. Oh, yeah, sorry. Oh, sorry, I thought you were raising your hand. Cool. Good questions. Anything else? All right. Oh, yeah.
Mentioning something about the title and shipping period. What happens to say stellar effects or any other accretion info?
Oh, for this tidal stirring hypothesis in particular?
Why?
I mean, the main reason was because I was pretty sure this hypothesis was wrong. And I knew we could test it. You're right that it's probably much more complicated and it has to do because there are baryonic effects that we didn't really consider that would occur in any dwarf galaxy. I mean, like, to be honest, I think that's what's causing all of these dwarf galaxies to look so puffy, is they just don't have the stellar mass needed to sustain a disk. Yeah. Cool. All right, in the last, like, 10 minutes of this talk, how many more minutes do we have? 10 minutes?
Yeah.
I think we have time for one more blast through of one of these. So, okay, you get to vote again on two different things. I can go back to talking about galaxy simulations and testing the resolution ladder, or I can talk about galactic archaeology stuff, which is totally different. All right, who wants to hear about number 1, galaxy simulations? And number 2, galactic archaeology stuff? Okay, it's an even split, but I know at least one person was extremely excited about the galaxy simulation stuff. This is for you. Okay, measuring galaxy properties is really hard. I think we can all agree on that. That's a pretty straightforward statement. But by difficult, I mean in the sense that the vast majority of our galaxy surveys in the near future are going to only be able to look at integrated light from galaxies. And so we have to understand how well can we actually get the properties of dwarf galaxies just from integrated light. So like I said, this is super important because we're going from SDSS. These are all the galaxies that SDSS observed in 8 years. These are all the galaxies that we got spectra for from DESI over the course of a few months. So we're orders of magnitude bigger data sets. We need to be sure that we can actually measure or infer galaxy properties in a reasonable way from these observations. And in particular, I'm going to start by talking about stellar masses of dwarf galaxies. It'd be nice to know their stellar masses, both because stellar mass shows up on a bunch of these sort of empirical galaxy relations, like the mass metallicity relation. So like it's a key independent variable that tells you something about the overall evolution of a galaxy. And they're also useful for cosmology. So if you look at the stellar mass to halo mass relation, it becomes incredibly uncertain below a particular halo mass at the low mass end. And that can help actually constrain cosmology. So it's actually kind of key for us to know the stellar masses of dwarf galaxies. And it's really hard to do that. So the way that most people do this is by, I would say non-trivial is the phrase that is typically used. It's hard to do this because you have to first model the stars in the galaxy, and then you have to model the effect of gas and dust in the galaxy. And if you put it all together, you get a model for the galaxy spectrum. But every single one of these things, then you can fit like the galaxy spectrum or the multi-wavelength broadband SCD of the galaxy, or even just measure a color of the galaxy and use some empirical calibration to give you a stellar mass. And the problem with all of these is that they break down when you start looking at dwarf galaxies. So when you do any kind of fitting, there's just so many assumptions that go into one of these fitting models. Like if you've ever used something like Prospector or Segal or Bagpipes, which is what all the JWST people use, you have to make approximately 10 gajillion different assumptions about the dust, about the star formation history of the galaxy, and they're almost all wrong for dwarf galaxies. They were all like, we know these things fairly well for Milky Way-like galaxies. We absolutely don't know what they're like for dwarf galaxies, and we definitely don't know what they're like in the high redshift universe. And then with these empirical relations, you run into the issue that these empirical relations were based off of these fitting methods and also tuned to match high mass galaxies, so Milky Way-like things. So they just fully break down at low masses. So one way to actually test our ability to recover stellar masses is to start with something where we know the ground truth. So we can start with a bunch of different simulations. And the idea is all simulations are wrong, but if you get enough of them from different people, then presumably that will tell you something overall about low mass galaxy physics. So I made friends with a lot of simulators and made them give me their simulated dwarf galaxies. So they range in complexity. So Grumpy is like a semi-analytic model. Universe Machine is this like half semi-analytic, it's a galaxy halo connection model. And then Marvel and Fire are both hydrodynamic simulations. So the idea is they're all wrong in different ways. We take these simulations and we make fake observations, and then we can see what observed masses we get. And then for all the simulations, they're simulations. So we know the ground truth masses. And this is a sort of direct test of how well our measurement techniques work on these fake galaxies. So I'm going to show a bunch of plots that look like this. They're just residual plots. Ideally, the residuals are small and also random. That's the ideal case. As you can see, if you actually try to apply like these empirical relations, they are not in fact small and random. You start getting pretty significant mass dependent effects for some of these empirical relations, especially if you like look at near infrared. So that's probably not good. Maybe we shouldn't use these for measuring dwarf galaxy masses. And then if you start looking at more complex fitting codes, so for example, if you try to do SED fitting, it depends a lot on the input assumptions that you put into your SED fitting model. So if you give it a star formation history, that's this nice parametric, like exponential decay star formation history, which is sort of what's classically used for massive galaxies, you do a bad job often. So for example, if you assume a constant star formation history, you do a really bad job by like orders of magnitude. This is on log scale. If you instead allow the star formation history to be non-parametric in the sense that you put it into a bunch of bins and let the bins vary, you can do a little better. And the exact shape of your prior assumption on star formation history doesn't matter quite as much. And then, so the whole point of this paper that we recently submitted was to basically test all of these different models and then come up with best practices. So we came up with a better empirical calibration that people can use. We are warning people in advance that if you're going to try to fit dwarf galaxies using this kind of SED or spectral fitting, you should really be careful about the assumptions that you put in, especially regarding dust and the star formation history. And this is still ongoing work, especially this is super popular now because JWST has found a bunch of galaxies, well, let me rephrase. The whole JWST breaking lambda CDM thing was because JWST found a bunch of really massive, really bright galaxies in the very early universe. And people have tried to explain this by saying, oh, these dwarf galaxies just have bursty star formation histories. So we're catching them when they're at the peak of their star formation burst. But the way that we measure burstiness usually requires some like this kind of SED fitting, which is wrong. Definitely in local dwarf galaxies and almost certainly in high redshift galaxies. Yeah.
Things like the dust attenuation matter a lot, and there's dust attenuation in all of the models is going to be somebody's version of dust attenuation probably calibrated to the current universe, large galaxies. How often can it be that even within this endeavor, you're comparing against things that are representative of
Yeah, that's a good question. So when we made the mock observations, we actually put in the dust attenuation law by hand. So we know what it is. We picked like a Calzetti attenuation law and then tried putting in different, so we know what it was going in. And then when we actually apply these various SED fitting techniques, we put in different attenuation guesses, different guesses for the attenuation law. And we can see like how badly does it change the stellar mass if your guess about the dust was totally wrong. So you're right, it's not perfect. It's not like full radiative transfer. I think that's the next step, is to see, if you change the dust attenuation law with like a full radiative, like 3D radiative transfer code, can you get anything reasonable out of it? My guess is probably not. I think SED fitting alone is not enough. And you probably also need far infrared to constrain anything about the dust. But that's a good question. It's a very controlled experiment in this particular study. Cool. So that brings really quickly in the last 2 minutes I have, we're trying to figure out why it's so hard to fit dwarf galaxies. We think it has to do with this star formation history, which is also supposed to be very bursty. So this dark line here is one of the star formation histories from one of the simulations that we looked at, from Grumpy in particular, I think. So we took the star formation history, we tried smoothing it out to see if it would affect the stellar masses that you get. This is still ongoing work, so we're pretty sure it doesn't change the color very much, but it's possible it would affect the actual spectrum of the galaxy. And so maybe if you do full spectral fitting, you can say something about the burstiness. And so that would be really helpful, not just for studying dwarf galaxies in the nearby universe, but also these really bursty things in the high redshift universe as well. All right, I blasted through that really quickly. There's a bunch of other things we can do. So not just looking at integrated light, but also, we can compare resolved and unresolved measurements using simulations. So a student that I've been working with recently has been taking these various dwarf galaxy simulations, changing the physics in those simulations, and making these mock IFU data cubes to see, can we recover any information about the stellar kinematics of these galaxies? The answer is probably not with existing IFUs, actually. We just don't have the spectral resolution to look at really ultra faint, low mass things. But this is ongoing work, so this is all top secret. Pretend you didn't see it. And then just to briefly summarize this last bit, simulations are a great way, I think, to test this resolution ladder, because we know the ground truth in a given simulation. And so we can test sort of individual rungs of this ladder, like how well we can recover properties from integrated light. And we can test how well we can compare resolved and unresolved measurements using fake IFU data. Okay, I'm so sorry that last section was a bit rushed, but hopefully that appeased your curiosity about galaxy simulations. Nice, okay. And with that, I think I'll take any questions about any of these 2 parts. Thank you so much for having me.
Thank you, Megan. We already had some questions, but we have a little bit of time if there are any others.
Yeah.
So this last part you talked about is really trying to get at the uncertainty of the mass, the stellar masses. Right? But the part we showed, we were looking to see if there is some, trend in the rotational support versus stellar mass.
Oh, yeah.
How, if you had to sort of draw an error bar on some of those galaxies, there's the uncertainty in their stellar mass, kind of roughly how big is it?
Okay, so the uncertainty in the I see what you're talking about. Yeah, the downside of doing the choose your own adventures that I actually don't know where it was. Okay, perfect, great. We're here, we're good. No, we're not good. All right, so to repeat the question for folks on Zoom, the question was on the uncertainties on this relation when we were talking about this thing, this one. So what are the stellar? Yeah, so we do have error bars, but these error bars are almost certainly underestimated, actually. They're probably larger. They should be larger based off what we now know about SCD fitting.
And were they included in the fit?
Yes, yeah. Well, we tried. It's a degenerate problem when you have, variance in both directions, both X and Y directions, and some intrinsic scatter. So we tested a bunch of different methods, and this fit for the most part is our best attempt to include both. Yeah. Good question.
Chris, what's known about the H1 content of this galaxy?
Yeah, that's a great question. I think there's this void galaxy survey, which looked at the H1 content of, I want to say 10 of these galaxies, 10 void dwarf galaxies. And several of them did not appear to have a lot of a big atomic gas reservoir. Some of them did. The rotation curves were not great. We did want to compare the H1 rotation with the stellar rotation of these things. But for the galaxies in our sample that overlapped with that sample, the H1 rotation curves, the resolution was not great, and we didn't trust them. That's a good question, though. And there is a survey that's doing some follow-up with CO, so I guess not atomic gas, but with. Yes, yeah. No, I think that's a good point. So that if anyone wants to write a VLA proposal with me, That might be a good one.
And also, sorry, what in voids, what range of stellar masses in practice are you being able to?
When we look at void dwarf galaxies, that's kind of up to us. I mean, so in this particular sample, we were looking at 10 to the 7, 10 to the 9 stellar masses. You could go more massive. There's a new IFU survey that's doing 10 to the 9 and above. You could, in theory, if you had enough integration time, you could go lower mass.
But then, I am that you're going to be able to start putting presence of events.
Yes.
And is there any evidence?
For
you know, companions?
around more massive dwarfs. Yes, actually. So this very recent, and there's this other IFU survey that I didn't really talk about because they focus more on massive galaxies than dwarf galaxies. But they actually literally just put out a paper today showing a dwarf merger. So 2 10 to the 9 dwarf galaxies that are merging with each other in a void. So I think it's unclear how frequent those kinds of interactions are, but it's pretty clear that they are important, even in void environments. Yeah.
Okay. Let's thank Mia again. Cookies and more opportunity.